Hello and welcome to this edition of What's New in SOLIDWORKS 2016. This is our Wednesday webinar for November 4th. So first of all, before we get into the actual presentation, I want to talk about something that may be of a cause of some confusion, and that is with respect to the SOLIDWORKS simulation packages. And also, this is going to alleviate some questions about which package I'm actually using for this demonstration. Now, starting with the standard package, of course, we have linear studies such as static assemblies. We can do some trend tracking. Of course, we can do a design study, some basic time-based motion, and so on. A little step further beyond that, we're still in the range of linear, but now we're looking at some more capabilities. Now we can get into frequency buckling, adding in some temperature analyses with the thermal, and of course we can look at optimization and different ways to simplify our model. Now, taking that even a step further is getting into nonlinear. So of course, nonlinear also has tools for analyzing buckling and of course input frequency and so on. But that's what we're going to be looking at for, of course, static and nonlinear. That's going to be the bulk of what's involved in terms of packages for this stress analysis showcase. Now, with respect to the rest of what's available in SOLIDWORKS Simulation, we also have SOLIDWORKS Flow Simulation, and within that there are extra modules for electronic cooling and HVAC. We do have a webinar series coming up on flow simulation, and that's going to be coming up over the next couple of weeks or so. And so what's our agenda for today? So we're going to be looking at a few things. Of course, there are more beyond this, but these are the ones that I really want to delve into and get into a lot of detail. The first part of that is the blended curvature-based measure. Now, we've seen two types of measures so far. There was the first one that came out, that was the standard measure algorithm, that is, and then we had afterwards the curvature-based measure, and now we have a new type of measure that we can utilize, and that is the blended curvature-based measure. Beyond that, we have mesh sectioning, something that a lot of people have been wanting to look at. It's a great way for us to get into our model and really look at the mesh elements and see if we have the correct element size and density in the right areas. Beyond that, we have intermittent fixtures and loads. So it's being able to turn on your loads and fixtures and then turn them off at certain intervals within your analysis. There was a workaround for this before, but now it is a dedicated tool. Now, next after that, we have finding under or unconstrained bodies. So this used to be just a case of a failure in the analysis, and it just stopped, and we had to go through some ways to find out which parts are under restrained. Beyond that, of course, we also have the edge shell gap size. So we're able to now set up a tolerance for any gaps in between edges and shell faces and edges and solid faces of shells. So we can get in there and have a lot more control over our parts. So let's jump directly into the first aspect that I want to talk about, and that is the new blended curvature measure. Now, it's arguably very efficient over the older ones, and that comes down to the number of elements that it utilizes. And I'll get into more detail of that once we open up the software. But it also is essentially it is an improved algorithm, which does improve efficiency, and we also have multi-core utilization, just like before with the curvature-based measure. It still utilizes the multi-core system. Now, in order to get into that, let's look at within SOLIDWORKS. Now, for those of you who are not familiar with SOLIDWORKS 2016, if this is the first time you're seeing it, you'll notice right off the bat that the interface has gotten revamped for sure. So we have a nice clean interface, just clear silvers and blues. But beyond that, let's look at our part in question. Now, if you have attended any of our what's new or the rollouts that we've done in various locations, you may recognize this part, our HRS 9000 Hawkeye. I know it's very nerdy kind of name, but that's the way we roll. So let's take a look at our frame at the bottom here. I'm going to get a closer look at that. Just for comparative sake, I want to first start off with the curvature measure. Let's take a close look at what that looks like. Let's show our mesh. It's an excellent measure. However, as we can see, if I get close into where all these curves are, we have, arguably an excess level of detail around these curves. So we have very, very small elements around these curves, but then in these larger kind of flatter areas, we have a coarser mesh. What ends up happening is that we have a lot of details in areas that we may not be able to utilize or even need, and overall, it's quite inefficient. For example, if I jump in here and look at the details of our mesh, we can see for our curvature measure, we have around 68,000 total elements. So, okay, it's arguably quite high for an element like this or a part like this. And just for comparative sake, I'm keeping our maximal element size here for these two comparisons the same. So it's going to be a 0.17 inches. So that's going to be the same, just for to get a real sense of how these respond. And we also see an aspect ratio there of 97% in terms of how many elements have an aspect ratio below 3. So that's very, very good. Still very good. So in terms of accuracy, in terms of quality of mesh and so on, still very good, but arguably not as efficient. So that's where the new measure comes in. First of all, let's take a look at the measure interface. If I go and create the mesh, we do have in the mesh parameters a new option here, of course, for the blended curvature based measure. And of course, just for comparative sake, again, the element size is the same. And if we take a look at what this mesh looks like, we can see, it's similar in a sense that we do have more details around the curves. However, that detail level is a lot less, and we have a much more reasonable dispersion of our elements. So we still have the details that we need around the curved elements in order to get the accuracy with respect to modeling our part properly with these elements. But again, the number of elements that we're dealing with, if I look at the details of our mesh here, has dropped from around 60,000 to around 40,000 total elements. Now, with respect to solver times, that is significant in terms of a drop. So we're still looking at a significant drop in elements, and the number of elements is a huge impact on your solver time as well as your contact sets. And the number of elements also affects your contact sets as well, because it's a node to node or node to surface type of thing there. So again, huge impact there with solver times. If we're looking at the aspect ratios, it's still very high quality elements, very similar as before. So we haven't lost any quality, but again, much more efficient. So looking back, back at the general setting here, we have a new blended curvature measure. Again, it improves the efficiency and still has a multi-core utilization. The way that it improves efficiency was back in the way that it disperses these elements. We still have a good density around curves and so on, but then the number of total elements has decreased significantly. Comparing that to the curvature measure, you can see quite clearly how small these elements are over here. Not particularly necessary. Still very good measure with respect to results, but still not as efficient as it could be. And just for giggles, let's look at the standard measure here. For the eagle eye attendees out there, you'll see that the element size here is actually smaller than the 0.17 that I was trying to stick to, and that's because the 0.17 element size will actually fail for this part using the standard measure. And that actually raises up another interesting point, and that is each one of these measures, along with efficiency improvements, also helps to run our meshing step a lot more smoothly. So here, where the standard measure failed at that element size, with the curvature measure, it was able to run. So we have a much higher probability of our parts being meshed. That means less failures in terms of mesh and so on. And again, looking back at the aspect ratio for our standard measure, only 85% of them have a lower aspect ratio of 3. So the quality of the elements has been improving, as well as the efficiency, as well as the probability that everything's going to run well. Getting on to the next section over here, still kind of in the with the flavor of meshes, and that is with mesh sectioning. So there are 3 new ways, arguably 2, but there are 3 new ways of actually viewing your mesh. The first way is to actually look at it. Let's look at a new feature in here. So within the mesh, we have this mesh quality. If I bring that down, it's a new type of feature. If we show this, essentially we just are showing our mesh. We do have several options in here. The one that I'm mostly interested in is this new mesh sectioning. So if I activate that, it works very similarly to a sectioning plot or a section view, sorry, and so you can select any kind of plane, and beyond that, actually, you can use a cylinder. So you can use a cylindrical volume in order to view your elements. So lots of interesting options there, and it works in the same way. So we can push and pull the plane back and forth, and this allows us to get really in depth and see through our part, and to ensure that in the areas of interest, we have the element sizes and the element density that we are hoping for. It adds in another level of control that we didn't have before. Now, that was the first way. I did mention that there are essentially three. The second one is arguably similar to the first. However, we do overlay the mesh with the actual stress plot. So any kind of plot that it's not, of course, it's not limited to just your stress analysis. You can do any kind of plot. If I right click on that, we can jump into a very similar tool for the mesh sectioning. So the interface and everything is exactly the same, except now it is interlaid or overlaid over the analysis. So we can see our elements, as well as the any kind of stress concentrated areas. And I like doing this because, for example, if you are finding these types of stress concentration areas, you can get in there and think about, well, do I need more information? So do I need more, more clarity in these areas with respect to the element size? So you can get in and very efficiently set up, any kind of controls that you want. So you can put in a mesh control around an edge, for example, and it's a lot more efficient because you're not putting it in areas of low concentration, and you are really focusing on what you need. The efficiency really comes down to, you can put tiny elements across your entire part and mesh it that way, but it's not, you don't need that that level of accuracy throughout the entire part. So now with our new mesh sectioning capabilities, you can have full control over your mesh to unprecedented levels and get really in there. And it's really exciting to be able to do that. Now, some people may not like this jaggedy aspect of it. Of course, it's, whatever element is touching the section plane, that is left alone. But beyond that, elements are essentially taken off. There's another way we can take a look at our mesh through a sectioning type of method, and that is instead of a mesh sectioning, we have a section clipping, right? So essentially, we're getting the same type of result, except it's a nice smooth transition. So it's just truncated right at that plane. We can view it with or without the mesh edges. And it's just, it gives you another option, another way to actually look at your parts and look at and analyze your mesh elements like so. So 3 new ways, very exciting in order to get in there, really have full control over your mesh. So that's very exciting. So mesh sectioning as a huge new function of SOLIDWORKS Simulation in 2016. Let's move on now, and we can talk about intermittent fixtures and loads. Now, you now have official full control of your fixtures and loads. Now, I say official because there are ways around this. You can, turn off a load by, I'm sure some people know the workaround, but then this is a built-in dedicated tool that we can now turn off loads and fixtures. This allows us to, we're eliminating, if we have a process, for example, if you have a clip that opens up, puts in, undoes, and so on. So if you have a huge process like that, you can analyze the stresses in different aspects, and you can get rid of artificial stresses that are, induced by loads or displacements that shouldn't be there at a particular stage. Let's take a closer look at that, particularly looking at a subassembly here in our quadcopter. So I'm going to open up our little side panel subassembly. Within this side panel, we can see that the panel is clipped on to these pins with these clips. So that's all well and good, and we can think of this as a potential issue with respect to, well, okay, is it a good design with respect to the 2 ways that we can put this onto its clips or onto the pins. We can either pull this piece and just yank it off. That's one way of doing it. Or we can analyze it the other way, another way. I'm sure there are more. But let's look at one way. So that's a kind of a direct pull kind of method where we're taking this piece, and all there is to it, if I look at the setup here, if I edit this definition, is we have a displacement essentially in the x-axis here of about 10 millimeters. So we're taking this plate, moving it out in the x direction, 10 millimeters. Okay, that's one way of doing it. And it's a pretty straightforward type of analysis. It is a nonlinear analysis. However, if I take a look at our displacement here, we can, let's animate that. So it's just pulling it right off, and there you have it. So really not much going on there, but then it's not really the best way of doing this. It could take or it could induce undue stress on the actual system itself. Not very ideal. But what if we had kind of a multi-phase type of analysis that we wanted to run? So say, for example, if I jump in here, if we wanted to space these clips out first, if we wanted to space them out and then start pulling the back panel afterwards. So if we wanted to do that, then we'd have to do something that was very, very difficult before. But now, if I jump into, for example, the first situation, which is very similar in the first study. However, instead of just a linear variation, we do have a curved type of variation in a way that in the beginning, as you can see here, we can turn this fixture off completely. So we have this new option, we can turn them off. That wasn't available before, which is now a dedicated tool, which is fantastic. So the fixture is off in the beginning, and then about after 10% of the solver time, it starts activated, and then by the time it's done, it moves by 10 millimeters in total. So that's the first piece of the puzzle. The second piece, of course, is the two displacements of the clips. We have the one side here that's going to be pushed out by a millimeter, and then the other side on the opposite direction here for these two faces pushed out in another a millimeter in the opposite direction. So how do we set that up? Now, in a very similar way, by utilizing that time curve and turning on and off fixtures, in the beginning, we have that we have it started. So by about 18% of our solver time, it's completely open. And then at around 35%, it's turned off. So the clip's open, it starts to move out, and then the clip is released. In this way, we can get really, really in depth and take a look at how everything is displacing and the type of stresses that are being induced at very specific times. Let's just check out the animation. So this gets opened up, and then it moves out, and then the clip is completely moved out. So very interesting, very easy and seamless now, so we don't have to do any jury rigging or anything like that. It's a built-in dedicated tool, which is very nice and exciting for those, I'm sure for those who have been looking for doing this, it's very exciting indeed. So what does this do? Again, allows us to eliminate those artificial stresses and just has a dedicated way of getting us to get more complex simulations running. Moving on a little bit, we're going to be looking at a bit of change of pace. We're going to look at under or unconstrained bodies. So up to this point, if you had something that was under constraint, you'll run your analysis, it'll fail, and it'll just tell you that it failed. So a couple of things that is a little bit not optimal there is, number one, the error message. It just says it failed and that's it. It doesn't tell us a whole lot. So now in 2016, as I'll point out, there are better error messages in a sense, and also there is at the end of soft springs. So and I'll get back to that later on. I'll let you guys decide whether you think it's the end of soft springs or not. But before that, let's jump back into our analysis here. And in fact, we're going to look at a crane analysis. Okay, so we're going to be looking at a crane analysis here. So essentially we have a multi-body part, multiple components and so on. So, you know, a weldment structure, and there's a lot of cases where you may want to look at this. If you don't want to use joint or beam elements, you can estimate it as shells. There's nothing wrong with that. It's actually quite a good idea. And so you have your situation like this. You have your design, everything's ready to go. Set up your fixtures and the loads and so on, and you get excited. You start running, and you call over your friends and you say, "Hey, check it out! You know, you want to check out some simulation?" And it's running. You get excited, but then it stops, and you get an error message saying model is unstable. I'm sure we've all seen this before, and it's particularly with a model of this size or larger. You may not have everything constrained properly. So this used to be all we used to get before, but now we also have this new link here that allows us to go directly into the SOLIDWORKS knowledge base and directly to an area that is relevant to this particular error. So rather than just this model, this error, and that's it, it brings us directly to a knowledge base so we can try to get some more information. So it did fail, and that's fine. If we wanted to get a little bit more information about why this has failed, there's a few things that we can do. But looking a bit closer, if I look here, we can see that there's in fact a gap between these beams. Maybe this was done for a weld gap, for example, which is fine, but of course it does affect our analysis. So unfortunately, our global contact set wasn't catching all of those gaps because they weren't contacting, they weren't coincident, so it didn't catch it. So what we'd have to do before is to try to go through those and apply those contact sets one by one. However, if I wanted to also take it a little bit deeper and say, well, okay, if I wanted to find out, is this the only problem or not, then I can actually look into this a little bit further and say, well, I can jump into my contact visualization plot. And before, when we were just looking at, okay, we can say what's bonded. If you are familiar with SOLIDWORKS 2015, you will be familiar with the contact visualization plot, I hope. And you can see whether the proper elements are bonded or not. But now we can take it a step further and say, let's look at any under constrained bodies. So we can take it for the entire assembly or the entire multi-body part and calculate. So rather than running this system either with, like a troubleshooting method such as a soft string method, which I'm sure if you've taken simulation class with us before, you would be familiar with that. You can now run this, which is a lot faster because it's simply looking for under constrained bodies, and it does group them up in groups. So every single component is termed as a group, and it tells us which degrees of freedom it has. So here, this group 1 unfortunately has every single degree of freedom that you're able to have, and it does give us a lovely little animation of that, so all rotations and all translations. And it looks like pretty much there is a large number of bodies that are under constrained here. So again, if you're able to figure out which bodies are under constrained is one thing, and then figuring out how you need to constrain it. So we've seen that there is a weld gap, and it's not just unique to that bottom section. Each one of these does have a weld gap. So we're going to have to go in and set up before you would have to set up a local contact set between each one of these. That's before. Now, though, if I look at the global contact feature, we have a little bit more information. So we can edit that. We can edit the feature, and we can look at here. We have an option for non-touching faces. So we can set up a tolerance of whatever we choose, and say, okay, so anything that is within this tolerance, if there's an edge. A shell edge and a solid face or a shell face, then just bond them. Just consider them to be bonded. Or, of course, it doesn't have to be bonded. You can use whatever contact type you like. So I can set that up here. I can say, okay, those gaps, consider them closed. So now that I've figured out the problem, I can rerun my mesh, something that would have been very daunting before. Running my simulation, finding out or restraining or fixing all of those bodies and so on is something that is really rather easy. And now I can run it, and now we have our results. So a lot of very exciting things there, new ways of visualizing what is under restrained, then also new ways of fixing the parts that need to be fixed, such as, you know, if we have weld gaps and so on, which is really quite common. So again, is it the end of soft springs? Of course, we do use soft springs for other methods, but of course, but one of the reasons that I would personally use soft springs is to check. You know, you'd run your analysis before. If something is under restrained, you turn on soft springs. You run it again, and you know, you look for the displacement plot. And if something is moved, you know, in the x direction by 1,000,000 inches or whatever, then that's obviously under restraint. So no more of that. A lot more efficient. Check for under constrained bodies, and you're done. So what else is there? These are some of the parts that maybe I'm not going to get into too much detail, but still very interesting to talk about. So the bolts and pins, we can set them up now on one part rather than a requirement of having to set the beginning and the end on two separate components or even three separate components and so on. So now we can have it on one part. And this is available for several different types. So we have the standard and counterbore with the nut, countersunk with nut, standard and counterbore screw, countersink screw, and so on. All these details, of course, can be found in the What's New document. So I don't want to bombard you with just lists and so on. That's not that exciting. Let's get into something that is a little bit more exciting than lists, and that is, well, we can now do equation-driven results. So the equation-driven results, say for example, if you have your analysis running and you have your own failure criteria. So you don't really particularly like the von Mises criteria, and you want to use your own. So now you're not restricted to the plots that are defined here. Now we can actually take it a step further and use the results equations tool. So we can take anything that we like. So say, for example, I'll take my von Mises, but I don't like it because it doesn't include, say, for example, my contact pressure, right? There would be no contact. But anyway, so if we wanted to do something like this or whatever it is, or if you wanted to subtract, you can do that rather easily. Set up your own type of plot. And here we have our new type of equation-driven, our own results criteria. And of course, we have all the same wealth of options that we had before. We can show min annotations, max annotations, and so on. So all the great tools of visualizing your stresses, but now with unique plots that you can define yourself. So something that's very exciting indeed. So equation-driven results. And now, of course, that brings us close to the end of what I wanted to talk about. Just as a recap of what we were talking about, the first new thing that we discussed was the fact that there was a new type of measure in the SOLIDWORKS simulation, and that is the blended curvature based measure. Now that is you know, it alleviates some of the excessive detailing around curved areas that we would see for the curvature-based measure, and that means that it's more efficient, you know, with the utilization of less elements, and it still fully utilizes multiple cores, just like the curvature-based measure. So, as efficient, even more. Very nice to use. We do have a new tool for mesh sectioning. We weren't able to do that before, but now we can ensure that we have, you know, the desired mesh density throughout our entire model. It gives us unprecedented control over our mesh with respect to getting the elements the right size where we want them. And you know, we have our intermittent fixtures and loads, so turning on and off fixtures and forces. And that, of course, eliminates artificial stresses. We can analyze much more complex types of analyses and so on, sequencing actions. And then we can look at something a little bit different, and that is the finding under constrained or unconstrained bodies, rather than, you know, just having it fail and that being the end of the story. We can now run a new type of analysis where it shows us the bodies that are unrestrained and then the degrees of freedom that they have. Beyond that, of course, we have the edge shell gap size, so we can set up a tolerance for any kind of gaps that we have for shell edges and solid face or shell face interfaces, and set that tolerances that are let that take care of any kind of problems that we have there. And then finally, we do have equation-driven plots. Again, you know, it could be used for a multitude of different things, but you know, if you have your own failure criteria, then you can use it for that. looking at other types of webinars that are coming up. On November 11th, we have the PDM webinar coming up, and then we also have the part 2 of the SolidWorks features. That's on November 11th, and then on the 18th, we have the Composer, MBD, and Inspection. So that's the technical communication, communicating your designs and changes and so on. And then finally, we do have for simulation, the flow packages, so that's flow simulation, and then we also have added to that the plastics. So thank you very much for attending this webinar. I hope that you found it very informative. If you do have any questions, please either send them to myself, or you can find the email to our support system. Of course, you can find this and other recorded webinars on this website here, hawkridgesys.com/events. /recorded webinars. Thank you very much for watching this, and you guys have a great day.